Hello, this is Dr. Liu. In this video, I will discuss heat engines. So heat engines are, for example, cars engines or steam engines or turbines. So these things are related to heat. Our goal is to generate some heat, typically above the ambient temperature, and try to harvest some work out of the engine. That's our goal. We want some work done to say push our turbine to generate electricity or maybe move our car forward. So that's what a heat engine does. It takes some heat and then it generates a certain amount of work. So let's theorize that in a block diagram. So here's a T high temperature source. So what this could be, it could be hot steam, right? It also could be the engines, the burnt fuel that's at very high temperature. And then we'll draw another block. This is our engine. And then the third block, this is, imagine the exhaust into the ambient, into the well, a low temperature reservoir. So we imagine these two temperatures are really relatively different. So the high temperature is quite high and low temperature is relatively lower. So here's what we expect to see. We draw some heat transferred into our engine from the hot steam, for example. So we transfer some heat into the engine, and we expect some work to be done by the engine. So here's some work output. But here's the catch. We cannot turn all of that heat absorbed by the engine into work. We have to exhaust some heat. So there's actually this path here. Some heat gets transferred out of the engine. So if you connect these lines, so that's what it looks like. It's like it's like a highway. So there's this one pass. So it gets this pass here. This is what we really desire. We turn some heat we absorbed from this high temperature source into work we want. But this is the other kind of undesired pass, but it still has to take place. Some of that heat transferred into a low temperature reservoir, so that's the some of the heat that we lose. So in this way, we can define an efficiency. And the efficiency is defined as how much work we can harvest compared to how much heat that was sent by the high temperature reservoir. For example, we burn some fuel. The fuel actually results in a certain amount of heat released. So this is the efficiency. And according to the first law of thermodynamics, we have work done equals heat from high temperature source to low temperature source. This is basically because we have cycles. So the cycles mean this engine has to keep running, right? It has to keep running. That means within the cycle, it absorbs some heat from high temperature source. It exhausts some heat to the low temperature source, and it produces some work. And it will be back to its original state, ready to absorb more heat and exhaust more heat, and also generate more work. So in the sense that the system, the engine system as a system, its internal energy isn't changing. It's just it takes something in, splits into work, and exhausts heat, and then it takes in again, splits into work and exhausts heat. So the internal energy isn't changing. That means the work it does has to be equal to the difference in the heat it absorbs and the heat it exhausts. Right. So that's this reason, according to the first law of thermodynamics, and also engines working in cycles, just basically repeating itself over and over. And we can rewrite this efficiency as work done. So this is Q high minus Q low, and then divided by Q high. So this is just another way to express an actual engine's efficiency. And the engine's efficiency, like I said, there's always this path. It has to exhaust some heat. So how much does it exhaust? There's actually an ideal situation where the maximum efficiency is specified, so that if you make some engine, this efficiency will be something you cannot exceed. So this was established by Carnot, and here's what Carnot did in his argument. So let's draw two isotherms, so two temperatures. So this is a lower temperature, this is a higher temperature, and we'll use a different color for the process. The process has to be cycled, so it basically is a closed loop. So we start from here, A. So this is low volume, high pressure, and we slowly expand at constant temperature from A to B. So this is an isothermal process. So in this isothermal process, because the temperature is constant, the internal energy doesn't change. So if the fact that the gas expands and doing work, increasing its volume, right? It does work. It has to absorb some heat to compensate for that work it did. So there's actually a Q high. It absorbs heat from the high temperature source because it's at high temperature, has to absorb that in order to do work. And then start from B, it does this adiabatic process to drop to a lower temperature, so it ends at C here. And this adiabatic process has no heat transfer, as we know. Two possibilities: one, you do it really quickly, but this is not the case. The case that Carnot assumes is you do it slowly with complete thermal insulation, so you don't lose heat, you don't gain any heat either. So no heat transfer, adiabatic. Okay, so that's the second pass, and then from C, it goes up, it gets compressed, the volume actually drops until it reaches D. Okay, so in this process, the volume is dropping. That means the work the gas does to the outside is negative. The outside does positive work to the gas, right? So that means the gas actually gains an internal energy, but it cannot increase internal energy because it is running along this isotherm. So internal energy doesn't change. So if it gains energy by work, it has to exhaust heat to lose all that energy gains by work done on it, so that it doesn't change its internal energy. And then through one final process, this is another adiabatic process. So let's mark this as isothermal. And this is adiabatic again. So over here, Q is equal to 0. Over here, it has to exhaust some heat because work is done to it, and it cannot increase internal energy. It has to dispense that energy in terms of heat. So this whole process is called the Carnot engine. And this can only be done theoretically, because this very slow process of isothermal, it's just not it's not practical for engines. So on the other hand, what Carnot engine gives us is an ideal efficiency. The ideal efficiency is the highest amount of efficiency that can be obtained by any engine. So this is determined by the high temperature, the low temperature, and then over a high temperature. So if you compare these two expressions, they look really similar. Heat absorbed at high temperature over heat exhausted at low temperature over heat absorbed from high temperature. And then this ideal case is high temperature minus low temperature over the high temperature. So basically, all of the actual engines will have efficiency less or equal in a very optimistic way that equal to this Carnot engine's ideal efficiency. All right, so let's do a couple of examples of efficiencies and ideal efficiency. So let's start our examples here. So first one, we want to do just an actual engine of 25% efficiency engine. That's actually relatively high efficiency for cars. What it does is it outputs an average of 20,000 joules mechanical work per second. Okay, so it does this, and our question is, how much does it absorb from the high temperature reservoir per second? And also, how much does it exhaust to the low temperature source per second? Okay, so because we're already aware of the efficiency definition, high temperature absorption minus low temperature exhaust over high temperature absorption, and we know that was given as 25%, so this is 0.25. And if we just cross multiply, we get Q high minus Q low equals 0.25 Q high. So what we can conclude is Q high, actually 0.75 Q high is equal to Q low. All right, so basically 75% of the absorbed heat gets exhausted, only 25% goes into work. Sounds miserable, but that's already a pretty good car engine in the current standard. So now we have this, and we also know that how much work it does per second. So in 1 second, Q high minus Q low should be the work done, right? It absorbs this much, right? It absorbs this much, exhausts this much, and it turns the rest into work. So this quantity is given to us, 20,000 joules. Okay, so what we can do here is we can turn this into Q low equals Q high minus 20,000, and then we can plug this into Q low, right? So now 0.75 Q high equals Q high minus 20,000. So Q high, 0.25 Q high is equal to 20,000. So Q high is equal to 4 times as big. So so divide by 25. So that's actually 80,000 joules per second. And then Q low is the difference, right? So 80 minus 20 is 60,000 joules of work. So that tells you if this is an actual engine, it takes in this much heat and exhausts this much heat, and the rest it does work. Okay, so let's go through another example about ideal engines. So what is the ideal efficiency? So what if we have a temperature at high temperature gas that we have as a working material? So at 500 Kelvin, we need to use kelvins for this for the Carnot engine calculation, and we have a low temperature 350 Kelvin. So what is the ideal efficiency? The best efficiency we can get from an engine. So this ideal efficiency would be equal to temperature high minus temperature low over temperature high. So 500 minus 350 over 500. So 150 over 500 or 30%. So from this we can see that the efficiency kind of depends, it depends on the difference between the two temperatures. If you can have a large temperature difference between the two sources, then you can have a slightly higher ideal efficiency. But this is pretty hot already. That's still relatively hot because you cannot really cool the exhaust below the ambient temperature. So this is still assumed to be a bit above the ambient temperature. So as you can see that ideal efficiency suffers is only 30%. So any engine that you run between these two temperatures cannot exceed 30%. Right. Thank you.